Hi everyone, welcome to Notes 4.4, Imaginary and Complex Numbers. Let's get started. Given I squared equals -1. So if I squared equals -1, that means that I is equal to the square root of -1. Now, this information right here is going to be super duper important as we go through this lesson. So if you need to remember that I squared is equal to -1 and I is equal to the square root of -1. Now, this is going to be how we deal with negatives underneath the square root. So when you did the quadratic formula back in Algebra 1, your teacher told you, hey, if you get a negative underneath the radical, that's no solution. Well, now that we're kind of a little bit past that, it's not really no solution, it's just no real solution. So if you end up with a negative underneath the radical of the quadratic formula, that means you have imaginary solutions. No real solutions, but imaginary solutions. So now let's talk about the difference in simplifying expressions versus solving equations when there is an I squared or an I involved. So if I have the square root of -4, the first thing I want to do is break that up into the product of the square root of 4 times the square root of -1. Because I know the square root of 4, the square root of 4 is 2. And now, thanks to those two handy equations at the top, I know that the square root of -1 is I. So that means that the square root of -4 is equal to 2I. Now, if I were to solve this, if I had x squared equals -4, no longer is this an expression, it's part of an equation. So to undo the square, we're going to take the square root of both sides. Well, when I take the square root of the left, I'm left with x. But when I take the square root of -4, we've already proven -4 to be 2I. However, we have to put plus or minus because we put the radical there. We did that. So since we put the square root there, we've got to have the plus or minus and then the 2I. Let's look at the square root of -75. Well, the first thing I want to do there is I want to break that up into the product of the square root of 75 times the square root of -1. Now, the square root of 75 is not a perfect square, so I'm going to have to simplify it. Well, I know 2 doesn't go into 75, but I know that 3 does 25 times. And then I know that 25 breaks down into 5 times 5. So I have 2 5s. So since I have 2 5s and this is the square root, they get to come out of the square root as a single 5. Because think about it, the square root of 25 is 5. And then the 3, they don't have a partner, so they've got to stay inside the square root. I also know that the square root of -1 is I. So how we write this is 5I square roots of 3. The 5 and the I will always, always, always go in front of the radical. Okay, so this is 5I square roots of 3. Now let's look at it in terms of an equation. If I had x squared equals -75, well, I would take the square root of both sides. Now, because I know that the square root of 75 is already 5I square roots of 3, then I can just add x equals and then plus or minus 5I square roots of 3. So, the moral of this story is, do not use a plus or minus when you're simplifying expressions. You only use the plus or minus when you're solving equations. So again, don't use the plus or minus if you're simplifying, but you'll want to use the plus or minus when you're solving. All right, let's move on. Let's look at this chart about roots. So they give us the two roots. They ask us for the axis of symmetry. And then they want to know, are those roots rational, irrational, or imaginary? So here's one thing. I know that roots are the same as x-intercepts. Roots are the same as x-intercepts. And I also know that the axis of symmetry is that vertical line of reflection that goes straight down through the middle of the parabola through the vertex. So what that means is that the roots are equidistant to the axis of symmetry, or the axis of symmetry is equidistant to each root. So looking at each of our examples here, let's look at the first one. So I know that I have a root of -5 and +2. Well, I know the distance from -5 to 2 is 7. So what I'm going to do is I'm going to take that 7, I'm going to divide it in half, and that tells me that -5 plus 3.5 will give me the axis of symmetry. It also tells me that 2 minus 3.5 will give me the axis of symmetry. So -5 plus 3.5, -1.5. 2 minus 3.5 is also -1.5. Now, could I have written x equals -1.5? Absolutely. Could I have written x equals -3/2? Could I have written it just like this? X equals -1 1/2? Yes, there are several different ways to express the same value. So here, our axis of symmetry is -1 1/2, or -1.5. Now it wants to know, are these roots rational, irrational, or imaginary? Well, they do not have an I, so they're not imaginary. They don't have decimals that go on forever, so they're not irrational, but that makes them rational. Let's look at our next example. 5 plus or minus the square root of 3. So we have 5 plus the square root of 3 and 5 minus the square root of 3. So remember, your axis of symmetry is in the middle, so let's just look at a number line to help us. We'll just draw the x-axis, if you will. So let's say right here is 5. So if I want 5 plus the square root of 3, this would be 5 plus the square root of 3. If I wanted 5 minus the square root of 3, this point right here would be 5 minus the square root of 3. So what is smack dab in the middle of 5 minus the square root of 3 and 5 plus the square root of 3? Well, it's 5. And here's the deal. If you have plus or minus something, your axis of symmetry is always going to be that first number. Always, always. Okay, let's look at our next box. It wants to know, are these rational, irrational, or imaginary? Well, 5 by itself is rational, but I'm taking that 5 and I'm adding the square root of 3 to it, or I'm subtracting the square root of 3. Well, I know the square root of 3 is irrational. So regardless of what's happening with that first number, anytime I add or subtract an irrational number, that is going to make my root irrational as well. All right, let's look at the next one, plus or minus 2i. Well, let's think about that. So I have a number line here, and I have -2i, and I have +2i. Well, what's right there in the middle? 0. So that means my axis of symmetry is x equals 0. Now looking at these roots, are they rational, irrational, or imaginary? Rational, irrational, or imaginary? Well, because I have the I in my root, that makes it an imaginary root. Now, let's look at 4 and 4. Notice that this is a double root. So really what's happening there is, if we have 4, what's happening is that vertex is at 4. That vertex is at 4. So that means that my axis of symmetry is going to be x equals 4. Now, Are these roots or roots, since it's the same one, rational, irrational, or imaginary? They are rational. And last example, 3 plus or minus I square roots of 2. 3 plus or minus I square roots of 2. Okay, so remember that little trick I showed you back up on the second example, that anytime you're doing plus or minus something, your axis of symmetry always goes through the number itself, the number in front. So that means that my axis of symmetry is going to be x equals 3. Now, are these roots rational, irrational, or imaginary? And I know what you're thinking. You're saying, well, the square root of 2 would make it irrational. True, but you've got this I in front. So since you've got that I in front, that beats everything. That's like, you know, the end all be all. So the moment you have an I, it doesn't matter what else is happening. It means that your roots are imaginary. All right, let's move on. Let's now move from our discussion of imaginary numbers to complex numbers. Complex numbers are written in the form a plus bi. A plus bi, where a is the real number and bi is the imaginary number. Now, it's always super duper important that you have it in the form a plus bi. For example, if I gave you minus 5i plus 3, the first thing you would want to do before you do anything else, is you want to flip it around to write it as 3 minus 5i. And we're going to see why that's super duper important here in just a second. But if we give you a complex number that's not in the proper form, the first thing you need to do is you need to flip it around so that it is in the proper form. And here's why. We're going to talk about forming the complex conjugate. So the complex conjugate is a minus bi. Now you will notice that to form the conjugate, all we did was we changed the sign between A and B. That's why it's super duper duper super important that you always have it in the right format, because if you don't, you're going to form the wrong conjugate and that's going to throw off all your problems. So always, always, always make sure it's in the proper form of a plus bi, so that when you form the conjugate, you can change it to a minus bi. Now, when do we use the conjugate? We use complex conjugate to simplify division problems where a complex number is in the denominator. So there are a few things you are never, ever, ever allowed to have in the denominator. One of them, 0. Another one is a radical. And then lastly, you may not have an imaginary or a complex number in the denominator. So we're going to use the idea of the conjugate to simplify it and get that complex or imaginary number up out of the denominator. Now, you may be wondering, well, what if my complex number is a minus bi? Easy enough. Your complex conjugate would then just be a plus bi. So if your complex number, a minus bi, then your complex conjugate is a plus bi. All you do is simply change the sign in between the a and the bi. So let's talk about operations with imaginary and complex numbers. So if I give you an expression that says 2i plus 4 minus the quantity 3 minus 5i, how would we go about tackling it? Well, in your mind, if it helps, think of the I like a variable. Okay, think of it like a variable that is representing the imaginary numbers. So the first thing I want to do is I want to distribute this negative, because if you don't, you will make a sign mistake. I guarantee it. So first thing I'm going to do is multiply that negative by the 3, and then I'm going to multiply it by the 5i. Now notice when I did that, I did not get rid of the symbol in between. I simply changed it to plus a negative and then distributed the negative to the 3 and the minus 5i so that I get plus a negative 3 plus a 5i. Now it's simply a matter of combining like terms. So 4 minus 3 is 1, 2i plus 5i is 7i. So that simplifies to be 1 plus 7i. Now let's talk about how do we multiply them. So if I give you something like 2 minus 6i times 3 plus 4i, you can FOIL it or you can box it. It doesn't matter how you do it. I'm going to FOIL it though. So 2 times 3 gave me 6. 2 times 4i gave me 8i. Negative 6i times 3 gave me negative 18i. And then negative 6i times 4i gives me negative 24i squared, because I times I is I squared. Now I see, well, we can combine some like terms right here. So 8i minus 18i is negative 10i. But wait, I squared. Think back to that second slide. What did we learn I squared is equal to? I squared is equal to negative 1. So I'm going to replace that I squared with a negative 1. And I'm then going to clean it up. So I get 6 minus 10i plus 24. And now I see, oh, okay, I can combine 6 and 24. So I can't go any further once I've reached 30 minus 10i. Now, let's see what happens when we multiply conjugates. So we're going to see why these conjugates are so magical. So let's look here. If I have 3 plus 5i times 3 minus 5i, let's see what that product is. Again, you can FOIL it or you can box it. I FOILed it, so 3 times 3 is 9. Negative 15i, that gives me positive 15i. And then 5i times negative 5i is negative 25i squared. What do you notice that happens to my i's? Well, negative 15i plus 15i, those cancel out. And I'm left with 9 minus 25i squared. But wait, I squared is negative 1. So I can sub in that I squared with a negative 1. So negative 25 times negative 1 is positive 25. And 9 plus 25 is 34. So, do you see why multiplying and knowing about conjugates is so vital? It does away with the i's. So anytime you multiply a complex number times its conjugate, you get rid of the i's. So this is going to be how we get rid of those i's in the denominator. So let's look. Okay, let's move on, and we're going to talk about division with imaginary numbers. So in this example, I have 5 plus 4i divided by negative I. Now we talked about on a previous slide how it's poor form to have a radical, an imaginary number, or a 0 in the denominator. Can't do it, can't have it, Okay, so that means I need to get rid of this I that's in the denominator. So what I'm going to do is I am going to multiply top and bottom by I. And that's because I over I is 1. So we're just multiplying by a special form of 1. We're not changing the value of the fraction. We're just changing what it looks like. Okay, and you may be wondering, well, why didn't you multiply by negative I over negative I? Well, I could have. negative I over negative I is still 1. But in the grand scheme of things, I guess, if you will, the negative, that's perfectly fine to have the negative in the denominator. The I is what you're not allowed to have. But again, if you'd rather use negative I over negative I, that's fine. Just be careful, watch your signs. So, but I'm going to choose to use I over I. So what that means is I'm going to distribute that I to everything in the top. So that becomes 5i plus 4i squared. Now in the denominator, I have negative I times I, which is negative I squared. But wait, I squared is something. Let's think back to that first slide. I squared is negative 1. So wherever I see an I squared, I'm going to convert that to negative 1. So up top, I end up with 5i minus 4. And in the bottom, negative is positive 1. So, but remember, we can't have it in that form. That's not a plus bi form. So I switch it around, and that becomes negative 4 plus 5i over 1. Well, putting something over 1, it's kind of pointless unless you're multiplying. So I'm going to change it to be just negative 4 plus 5i. Just negative 4 plus 5i. So now let's move on and let's talk about division with complex numbers. In this example, I have 3 plus 2i divided by 4 minus 5i. Well, we have imaginary numbers, or in this case, complex numbers, in the numerator and the denominator. Well, it's perfectly okay to have a complex or imaginary number in the numerator. It doesn't matter what goes on up in the numerator. However, in the denominator, we have a complex number, and that is not allowed. Now, you may be thinking, well, how does that differ from the previous example? Well, on the previous example, we just had an I. There was no addition or subtraction going on in the denominator. It was a monomial. So if your denominator is a monomial, you simply need to do I over I. But if you have some adding or subtracting a binomial, it's a complex number. If you have a complex number in your denominator, you have to use the conjugate. So you always form the conjugate of the denominator, okay? Don't worry about the numerator, okay? He's perfectly fine having imaginaries up there. But the denominator is what you form the conjugate of. So 4 minus 5i, the conjugate becomes 4 plus 5i. But if I multiply the denominator by 4 plus 5i, I also have to multiply the numerator. Because again, 4 plus 5i divided by 4 plus 5i is just a fancy form of 1. So again, we're not changing the value of it, we're just changing what it looks like. So now we're going to multiply these. So what I always do anytime I have binomials is I like to put them in parentheses so that way I don't mess anything up. Now you can FOIL or you can box, it doesn't matter. I FOILed. So I did 3 times 4 is 12, 3 times 5i is 15i, 2i times 4 is 8i, and then 2i times 5i is 10i squared. Then we did the bottom. 4 times 4 is 16, 4 times 5i is 20i, negative 5i times 4 is negative 20i, and then negative 5i times 5i is 25i squared. Well, first thing I'm going to do is I'm going to start combining my like terms. So I notice that the 20i's go away, and I end up with 12 plus up top 23i, but wait a minute, I squared is equal to negative 1. So in addition to combining like terms, I'm going to change those I squareds to negative 1s so that I end up with this becomes negative 10 and that becomes positive 25. So I get 12 plus 23i minus 10, and then 16 plus 25. One more combining like terms. 12 minus 10 is 2. 16 plus 25 is 41. So I get 2 plus 23i over 41, or if you'd like to break it up, you can also write it as 2 over 41 plus 23i over 41. Your choice. Our next example wants to know, is 5 plus I a solution, root or 0, of f of x equals x squared minus 10x plus 26? Well, whenever I want to know if something is a solution, root or 0 of a function, that simply means I'm going to plug it in anywhere I see an x. And so that's exactly what I'm going to do here. So f evaluated at 5 plus I is equal to 5 plus I squared minus 10 times 5 plus I plus 26. Well, remember back from our previous lessons, anytime we see 5 plus I quantity squared, so we see a parenthesis squared. Anytime we see a parenthesis squared, that means, hey dude, write me twice. Okay, again, don't forget that. Parenthesis squared always means, hey dude, write me twice. Now, I'm going to FOIL these two together, but then I'm also going to distribute that negative 10 because I changed my minus to plus and negative. So, and again, could I have boxed 5 plus I times 5 plus I? Absolutely, it's a matter of personal preference, whatever you're the most comfortable with. So 5 times 5 is 25. 5 times I is 5i. I times 5, 5i. And I times I is I squared. And then over here, I get plus negative 50 minus 10i. Now, let's combine some like terms. So I get, right here, those become 10i. So I get 25 plus 10i plus I squared minus 50 minus 10i plus 26. Ooh, what do you notice is going to happen? That's right, 10i cancels out with negative 10i. But I also know I squared is negative 1. So that gives me 25 plus negative 1 minus 50 plus 26. Now we just add left to right. So 25 minus 1 is 24. 24 minus 50 is negative 26. Negative 26 plus 26 is 0. So since I plugged it in and I got a 0 value, that means it's a solution root or 0. So yes, 5 plus I is a root. Let's talk about how we graph a number on the complex number plane. So right here, they're wanting us to graph negative 3 minus 2i. Negative 3 minus 2i. So here's what we're going to do. We're going to use our xy axis. However, instead of being x's and y's, you're going to let the x-axis be the real axis, and the imaginary numbers will be plotted on the vertical. So the real axis, that's the x-axis. The y-axis becomes the imaginary axis. So if I want negative 3 minus 2i, so to get negative 3, I'm going to move left 3 on the real axis, and then negative 2i means I'm going to move down 2 on the imaginary axis. So you can, in a way, think about it like a coordinate point. Negative 3 minus 2i. I go left 3 and then down 2i. And that's how I get my point. Now, if I gave you another point, let's say right up here, and I said, okay, what's the complex number that represents that point? Well, you'd go, okay, there's 1, 2, 3, 4, 5, 6, 7. So it's going to be 7, and then I go up 2, so that's going to be plus 2i. So it's really easy to go from the complex number to the point, but you can also do the point back up to the complex number. So the idea is the same there. Now, let's talk about finding the absolute value of complex numbers. Now remember, the absolute value is the distance from 0. So this is going to be the formula that we use. The absolute value of a plus bi is equal to the square root of a squared plus b squared. Okay, here's something that's really important that I want to draw your attention to. Never, ever, ever use the I when you're calculating absolute value. There will be no partial credit on this. So never, ever, ever use the I when calculating absolute value. If you do, you're going to get it wrong. You're going to get it wrong. So the absolute value of a plus bi is equal to the square root of a squared plus b squared. So if I have -3 minus 2i, then that means that my a is -3 and my b is -2. Remember, we do not use the I. So I'm going to plug that in. -3 quantity squared plus -2 quantity squared, and then we take the square root. Well, -3 squared is 9, -2 squared is 4. So 9 plus 4 is 13, and that's as far as we can go. We cannot simplify that radical, and it's not a perfect square. Let's look at another example. 5 plus I. So, well, that tells me that my A is 5, but it also tells me that my B is 1. Okay, so I'm just going to plug in, and again, remember, we do not use the I. Don't use the I, you'll cry. Okay, so square root of 5 squared plus 1 squared. Well, 5 squared is 25, 1 squared is 1, so that becomes the square root of 26. And that's all you can do with it. Again, it won't simplify. It's not a perfect square, so we leave it just like that. Okay, so this concludes your lesson 4.4. So now you will go to Canvas and you will complete worksheet 4.4. All right, have a good one, everybody. Please wash those hands, social distance, stay away from sick people if you can, and wear your mask, of course. Always, always, always wear those masks. So have a great one, and we'll talk to you soon. Bye, everyone.